In this presentation, I'll talk about temperature entropy diagram. Before entering into this topic, we should know the meaning of the term entropy. The entropy measures disorder of the system. Entropy provides the value of unavailable energy, which means that the energy which cannot be converted into mechanical work is called unavailable energy. A system's entropy is defined as the ratio of heat energy given or taken away from a system to its temperature. S equal to H divided by T. H may be the amount of heat energy either given to the system or taken away from the system. T is the temperature of the system. We know that in the case of Carnot cycle, 4 operations are there: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression are the 4 operations. During the isothermal expansion AB, the working substance absorbs H1 of heat energy from the source maintained at a temperature T1. In the case of adiabatic expansion BC, no heat is absorbed or liberated. During the isothermal compression process CD, the working substance rejects H2 quantity of heat energy to the zinc maintained at a temperature of T2. Then DA is the adiabatic compression process. During this adiabatic compression process, no heat is rejected or absorbed. So this is a pressure volume diagram. With the help of this PV diagram, we have explained all the 4 operations. This is temperature entropy diagram. Temperature is present along the y-axis, whereas the entropy is available in the x-axis. The line AB is isothermal expansion, BC is adiabatic expansion, CD is isothermal compression, DA is adiabatic compression process. We know that entropy is a constant in an adiabatic process. Therefore, see the 2 adiabatics, DA and BC. These 2 are the adiabatic lines. All along the adiabatic lines, the entropy is a constant. See the adiabatic B to C. The value of entropy is S2. Throughout this line, entropy is a constant. Then, if you consider the line DA, the entropy value is S1. In the case of isothermal expansion process AB, the entropy is increased from S1 to S2. CD line represents isothermal compression. Here the entropy is decreased from S2 to S1. So the entire Carnot cycle operation is represented by this rectangle ABCD. Now read out this. The isothermal AB, adiabatic BC, isothermal CD and adiabatic DA on the PV diagram represent the changes: isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compressions respectively. An isothermal state is represented on a temperature entropy diagram by a straight line parallel to the entropy axis. This is isothermal state which is parallel to the entropy axis, which means that the temperature is a constant. A straight line parallel to the temperature axis, y-axis is the temperature axis, represents an adiabatic. Adiabatics BC and DA, these 2 are adiabatic lines. Here they are parallel to the temperature axis. Therefore, entropy is a constant. On a TS diagram, temperature entropy diagram, the rectangle ABCD represents the Carnot cycle. The total Carnot cycle is represented by this rectangle ABCD on the temperature entropy diagram. Now we should talk about heat absorbed. See, this is isothermal expansion process. During this expansion process, the working substance is placed over the source and is subjected for expansion. Then the working substance absorbs H1 of heat energy from the source, which is maintained at a temperature of T1. Therefore, the entropy increases. Initial entropy is S1, final entropy is S2. So the increase in entropy is S2 minus S1, that is equal to H1 by T1. Now read out this. The entropy changes from S1 at A to S2 at B during the isothermal change AB. The value of entropy is S1 at the point A, and the final value of the entropy is S2 at the point B. As a result, the increase in entropy is equal to S2 minus S1. If the system absorbs certain amount of heat energy, the entropy increases. If the system rejects some amount of heat energy, the entropy decreases. If H1 is the amount of heat absorbed from the source at the temperature T1, then S2 minus S1 is equal to H1 by T1. This is our increase in entropy. From this, H1 is equal to S2 minus S1 into T1. This is equal to area ABEF. See here, ABEF, the total area, ABEF. This is heat absorbed. Now come to the next line, the line BC. This is adiabatic line. All along the adiabatic, entropy is constant. The value is S2, but the temperature decreases from T1 to T2. The entropy remains constant in the adiabatic expansion BC, so no heat is gained or lost. Next, heat rejected. The entropy changes from S2 at C to S1 at D in the isothermal CD. See, this is isothermal compression process. CD represents isothermal compression. Here the entropy is decreased from S2 to S1. At the point C, the entropy is having higher value S2. At the point D, the entropy value is decreased to S1. Therefore, the decrease in entropy is S2 minus S1, that is equal to H2 by T2. Because along this line CD, this is isothermal compression line, the working substance rejects H2 amount of heat energy to the zinc, which is maintained at the temperature of T2. If H2 is the amount of heat rejected to the zinc at the temperature T2, then S2 minus S1, decrease in entropy, equal to H2 by T2. From this, H2 equal to T2 into S2 minus S1, that is equal to area DCEF. See here, DCEF, this area. Thus, the area covered by isothermal CD and the entropy axis represents the heat rejected to the zinc in a Carnot cycle. See here, the area covered by the line CD and the entropy axis. This is the amount of heat rejected to the zinc. The area covered by the isothermal CD and the entropy axis represents the heat rejected to the zinc in a Carnot cycle. There is no gain or loss of heat during the adiabatic change dA. We know that dA is a adiabatic line. Here no heat is absorbed or rejected. but the entropy remains constant. The entropy value is S1. Now we should talk about available energy. Available energy means the amount of energy used to convert it into mechanical work. Available energy or heat converted into useful work is H1 minus H2. Now find out the value of equation 1 minus equation 2. This is H1, this is H2. H1 minus H2 is T1 into S2 minus S1 minus T2 into S2 minus S1. Take S2 minus S1 as a common term. We can get S2 minus S1 into T1 minus T2. So the interim step, if you need, you may put like this. This is equal to, if you put T1 minus T2, S2 minus S1, if you take out, you can get here T1 is present, here T2 is present. So H1 minus H2 equal to S2 minus S1 into T1 minus T2. Now subtract these two areas. The first area is ABEF. ABEF minus the second area, heat rejected area DCEF. ABEF minus area DCEF is equal to area ABCD. Now come to this diagram. ABEF minus this area DCEF. If you subtract the quantity DCEF from the area ABEF, we can get this rectangle. We may get area ABCD. As a result, the area of a Carnot cycle included on a temperature entropy diagram between two isothermals and two adiabatics represents the amount of available energy. This rectangle represents the amount of available energy. Available energy means the energy which can be converted into mechanical work. ABCD represents available energy of a Carnot's engine, that is the energy which can be converted into mechanical work. Now we have to calculate the amount of unavailable energy, the energy which cannot be converted into mechanical work. We know the efficiency of Carnot engine, eta equal to H1 minus H2 divided by H1, output by input. This is 1 minus H2 by H1, which is equal to 1 minus T2 by T1. Temperature of the source is T1, temperature of the sink is T2. 1 minus H2 by H1 is equal to 1 minus T2 by T1. From this, H2 by H1 is equal to T2 by T1. H2 is the amount of unavailable energy. H2 equal to H1 into T2 by T1. We know that H1 by T1 is equal to S2 minus S1. So H2 equal to S2 minus S1 into T2. The value H2 is known as unavailable energy. The energy which cannot be converted into mechanical work is called unavailable energy. The amount of unavailable energy is the product of the entropy increase of an isothermal expansion and the temperature of the zinc. It's all about the temperature entropy.